Our topic today is inverse trigonometric functions. We will define the inverses of three common trigonometric functions: sine, cosine, and tangent. You may want to refresh our study of inverse functions, specifically the conditions for which a given function has an inverse. Remember, it has to be bijective, that is, injective and surjective. Let's talk now about the inverse of sine. Let me draw the graph of the sine function, and we will discuss how to construct its inverse. Remember, sine is odd. Let's mark points of interest. Five pi over 2, 3 pi, negative pi over 2, negative pi, negative 3 pi over 2, 2 pi, negative 5 pi over 2. If we view our function sine x as defined on the entire real line and think about how to define its inverse, we immediately see a problem, because our function, considering the image and codomain to be the interval negative 1, 1, our function doesn't pass the horizontal line test. The line y equals 1/2, for instance, crosses our function at infinitely many points. And it's not clear which of these infinitely many values, this one, or 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 this one, we should consider to be the inverse of 1/2. For that reason, we resort to our standard technique. Remember, when we studied inverse functions, we often restricted the domains of our functions so that our function on the restricted domain passes the horizontal line test. That is exactly what we do in this case. If we restrict the domain of sine to be from negative pi over 2 up to pi over 2, and note that the image of that new function is still negative 1, 1, the sine function takes all of its values from negative 1 to positive 1 on this interval. And on this restricted domain, it is injective. And of course, it is surjective. If we view the codomain, to be the interval -1, 1. In other words, the sine function is bijective, again on this restricted domain, and being bijective, it has a unique inverse. If we fix any y between -1 and +1, and by inverse of sine of y, we put the unique x whose sine equals y, that is a valid definition. For example, in my picture, the unique x in between -π/2 and π/2 whose sine is 1/2 is π/6. There are in principle infinitely many other points where sine is π/6, where sine is 1/2, excuse me. For instance, 5π/6, -7π/6, -11π/6, and infinitely many more. But only one of them, π/6, belongs to the interval -π/2, π/2. So the definition is very simple. For any x in the interval -1, 1, arcsine x, which is the same as sine inverse x. I prefer the notation arcsine. The inverse of x, the inverse sine of x, is the unique number in the interval -π/2, π/2, whose sine equals x. That is a well-defined function, and we immediately see the domain of arcsine is the image of sine is the interval -1, 1, and likewise the image of arcsine is the domain of sine, restricted of course, is the interval -π/2, π/2. We can find some common values of arcsine. We already noted that arcsine of 1/2 is π/6, and we can explain why. since first, sine of pi over 6 is 1/2, and second, which is no less important, is that pi over 6 belongs to the interval negative pi over 2, pi over 2. What about arcsine of root 2 over 2? We know that's pi over 4, again for two reasons. First reason is that sine of pi over 4 equals root 2 over 2, and the second reason is that pi over 4 belongs to the interval negative pi over 2, pi over 2. Likewise, arcsine of 0 is 0, because sine of 0 is 0, and the 0 angle is in the interval. What about arcsine of 1? That is pi over 2. The only point on the interval negative pi over 2, pi over 2, where the horizontal line y equals 1 intersects the graph of sine, is the point pi over 2. So we have here that sine of pi over 2 is indeed 1, and pi over 2 belongs to the interval negative pi over 2, pi over 2. What about arcsine of root 3 over 2? We know that's pi over 3. That is, of course, because sine of pi over 3 is root 3 over 2, and pi over 3 is in the interval negative pi over 2, pi over 2. What about negative values of arcsine of negative arguments? Well, arcsine of negative 1/2, for instance, I claim is negative pi over 6. That is because sine of negative pi over 6 is, by the fact that sine is odd, negative sine of pi over 6, and that's negative 1/2, and also negative pi over 6 is in the interval. And likewise, arcsine of negative root 2 over 2 is negative pi over 4, since again, sine of negative pi over 4 is negative root 2 over 2, and of course negative pi over 4 lies in the desired interval. Arcsine of negative 1 is negative pi over 2. That is, of course, sine of negative pi over 2 is negative 1, and because negative pi over 2 is in the interval. Likewise, arcsine of negative root 3 over 2 is negative pi over 3. That is because sine of negative pi over 3, by the fact that sine is an odd function, is negative root 3 over 2, and of course negative pi over 3 is in the interval, negative pi over 2, pi over 2. In fact, our computations may make us wonder whether arcsine is an odd function. And the answer is yes. Let's see if we can actually prove this. Arcsine of negative x actually equals negative arcsine x for any x in the domain of arcsine which is negative pi over 2, pi over 2. And if we want to properly explain this, let me copy this to the next page. I don't know if we can properly explain this. Well, the explanation might be this. If x is in the interval negative pi over 2, then so is negative x, because that interval is symmetric about 0. And for any such x, sine of arcsine of negative x is of course negative x. And of course sine of the right hand side by the fact that sine is an odd function will be negative sine of arcsine x, and that's simply negative x. So we have from here that arcsine negative x and negative arcsine x are two numbers in the interval negative pi over 2 whose sines are equal. And because on that interval negative pi over 2 the sine function is injective, that implies that the fact that sine of arcsine of negative x equals sine of negative arcsine x, and sine x being injective on negative pi over 2, these two things imply that the arguments are equal. Arcsine negative x equals negative arc sine x for any x in pi over 2, negative pi over 2, pi over 2. So we know enough about the arcsine function to be able to draw its graph. Remember, the domain is negative 1, 1. Arcsine of negative 1 is negative pi over 2. Let's say this is negative pi over 2. Let's say this is 1. Arcsine of 1 is pi over 2. Arcsine of 0 is 0. The function is odd. Note that the sine function, if we were to graph it in the same coordinate axis, the sine function would look like this. Or perhaps that's not a very good idea, though. And that is the line y equals x. All right. So that is about arcsine x. Now we can do the same analysis for arc cosine x. Let's start with the graph of cosine x. Remember, the cosine function is even, so its graph will be symmetric about the y-axis. And much like for sine x, we see that cosine x doesn't pass the horizontal line test. If we again consider the line y equals 1/2, we see that it intersects with the graph of cosine x at infinitely many points. At pi over at pi over 3 and at negative pi over 3. What are the other points? Okay, this is 2 pi, 5 pi over 2. So there are other points, of course, other than pi over 3, where cosine is 1/2, pi over 3 and negative pi over 3. And the next point will be pi over 3 plus, just let me check the graph. All right, so this is pi over 3, then 2 pi, pi over 3 short of 2 pi, I believe. Cosine is again 1/2. So that must be 5 pi over 3. And that is then 2 pi plus pi over 3, so 7 pi over 3. And so on. There are infinitely many points on the graph where our line y equals 1/2 intersects with the graph of cosine, and it's not clear which one of these values, this one or this one or this one or this one, should we view as the inverse of 1/2. So the technique is the same. We simply know that the cosine function as defined on all of R is not injective. So by convention, we restrict the domain of cosine from the entire real line to a much smaller set, 0 pi. Note that the function on the set 0 pi takes all of its values from -1 up to +1 and is injective. It's monotone decreasing. So viewing the codomain, of course, as the set -1, 1, our function cosine becomes bijective, and therefore it has an inverse, a well-defined inverse. Viewed with domain zero pi and codomain -1, 1, the cosine function is bijective. And being bijective, it has an inverse. moreover, a unique inverse. That brings us to the definition, similar to the one we gave above. For any fixed x between -1 and 1, the unique number in the interval zero pi, whose cosine equals x, is called arc cosine of x, or sometimes cosine inverse of x. It is indeed unique because the function is now injective. Let's practice finding arc cosines of various values. What is, for instance, the arc cosine of 1/2? Of course it is pi over 3, and to check that this is pi over 3, we need to check two things. Well, first, that cosine of pi over 3 is 1/2, and second, that pi over 3 is in the interval 0 pi, which of course it is. What is arcsine of root 3 over 2? We know that's pi over 6. That is because cosine of pi over 6 is root 3 over 2, and, which is no less important, that pi over 6 belongs to the interval 0 pi. In a very similar fashion, we can find that arc cosine of root 2 over 2 is pi over 4. That arc cosine of 0 is 1, or maybe not. Arc cosine of 1 is 0. That is because cosine of 0 is 1, and because 0 belongs to the interval 0 pi. What about arc cosine of 0? We know that's pi over 2. That is because cosine of pi over 2 is 0, and pi over 2 belongs to the interval 0 pi. And likewise, arc cosine of -1 is pi. That is because cosine of pi is -1, and of course pi belongs to the interval 0 pi. Let us draw the graph of arc cosine. Note that our cosine is always non-negative. It only takes values in the interval 0, pi. So our cosine of -1 is pi. Our cosine of zero is pi over 2. And our cosine of our cosine of -1 is pi. Our cosine of 0 is pi over 2. And our cosine of one is 0. So the graph looks like this. There is some kind of symmetry here, although of course it's neither even nor odd. But I believe there is some kind of symmetry in the sense that you step away here by t and step away here by t. Or maybe not. Maybe these values are not expressible through each other. We would have to think. Anyway, this is the graph of arc cosine x. And the interesting fact here is that it's neither even nor odd. Cosine is even, but arc cosine is not even, unlike the correspondence between sine and arc sine, both of which are odd. And let's finally do the same analysis for tangent. Remember, the tangent function has asymptotes at pi over 2, at negative pi over 2, and then there is a branch between these two asymptotes. That's pi over 4. That's negative pi over 4. And other branches are a copy-paste of this one. Let's draw two more. So this is pi over 2. This is 5 pi over 2. This is negative 5 pi over 2. And there are infinitely many more branches like this. This is the graph of tangent x. And again, we see our function doesn't pass the horizontal line test. It's not injective if we view it as defined on the usual domain, all the x's except pi over 2 plus pi n, where n is an integer. If we, for instance, draw the line y equals 1, we see that it'll intersect our graph at infinitely many points. For example, at points pi over 4, at point negative 3 pi over 4, at point 5 pi over 4, and infinitely many more. All right, so the technique is the same as before. So we say that on its usual domain, which is the set x and r, except pi over 2 plus pi n, and an integer, the tangent function is not injective, so there is no way to define its inverse. So we restrict its domain to a much smaller set. By convention, that set is from negative pi over 2 to pi over 2. Note that the tangent function on this set takes all of its values, the entire real line, and is monotone increasing, and therefore injective. Being injective and having the entire real line as its image, this function has a unique inverse. And this brings us to the definition. For any x in the real line, the unique element in the open interval negative pi over 2 pi over 2 whose tangent equals x is called the arctangent. of x, or sometimes written as tangent to the negative 1 of x. So we have here, by the definition of tangent and arctangent being inverses of each other, we have that tangent of arctangent x equals x for every x in the domain of arctangent, which is the image of tangent, which is the entire real line, and likewise arctangent of tangent x. Equals x. This time it's for every x in the domain of tangent, restricted, of course, which is also the image of arctangent, which is the open interval negative pi over 2, pi over 2. So and we can actually say the same thing about arc cosine, cosine and sine, and arc sine. This here we did say it. Although we did say it here. Maybe I should say it more explicitly, that sine of arc sine of x equals x, and arc sine of x equals x. That's for every x in the domain of arc sine, which is also image of sine, which is simply the interval negative 1, 1. And arc sine of x equals x, that's for every x in the restricted domain of sine, which is also image of arc sine, which is the interval negative pi over 2, pi over 2. And the same thing for cosine and arc cosine is that cosine of arc cosine of x equals x, and arc cosine of x equals x. That is for every x in the domain of arc cosine, which is of course the image of cosine, which is the interval negative 1, 1. And this here is for every x in the restricted domain of cosine, which is also the image of arc cosine, which is the interval 0, pi. The same thing for tangent we just wrote. Let's practice finding arctangents of various values. We can find arctangent of 1. That's immediately pi over 4. Again, we check two things. That tangent of pi over 4 equals 1, and that pi over 4 belongs to the interval negative pi over 2, pi over 2, both of which are true. As we will explain in a second, arctangent is an odd function, so arctangent of -1 is -π/4. Arctangent of 0 is 0. That is because tangent of 0 is 0, and 0 belongs to the interval -π/2, π/2. There are some values of tangent that I don't remember. If we can recall them, for instance, what's tangent of π/6? That's sine of π/6, which is 1/2, over cosine of π/6, which is √3/2, which is 1/√3, which is √3/3. So that tells us that arctangent of √3/3 is π/6. Since tangent of π/6 is √3/3, and π/6 is in the desired range, -π/2, π/2. Likewise, arctangent of -√3/3 equals -π/6. We will check that arctangent is odd, for sure. Let's add a page. And I can also compute tangent of π/3, that's sine of π/3, √3/2, over cosine of √3, that's 1/2. That is √3. So that immediately implies that arctangent of √3 is π/3. And again, we're checking that tangent of π/3 is √3, and π/3 belongs to the interval -π/2, π/2. And also arctan of -√3 equals -π/3. Let's check that arctangent is an odd function. That is, arctangent of -x equals negative arctangent x for any x in the domain of arctangent, which is the entire real line. Well, in this equality we're trying to prove, both numbers are defined and both belong to the interval -π/2, π/2. So both numbers, arctan -x and negative arctan x, are defined for any x, and both belong to the interval negative pi over 2, pi over 2. Even this number, right? Arctangent is in negative pi over 2, pi over 2, but since the interval is symmetric about 0, whether you put negative in front of a number won't take it out of this interval. If this is x, this is negative x. If this is arctan x, this is negative arctan x. So because they're both in this interval, and because the tangent function is injective on this interval, it suffices to verify that tangent of both sides are equal. Tangents of both sides are equal. Well, tangent of arctangent of negative x is simply negative x. That's by definition of tangent and arctangent. And tangent of negative arctangent x, by the fact that tangent is odd, tangent is an odd function, simply is negative tangent arctangent x, and that is again negative x. So this verifies that arctangent is an odd function. Let's draw the graph of arctangent. It will be interesting for us to note that the vertical asymptotes negative pi over 2 and pi over 2 of tangent, when you reflect them above the line y equals x, become the horizontal asymptotes of arctangent. So because of symmetry, the vertical asymptotes x equals plus minus pi over 2 of the tangent function correspond to the horizontal asymptotes y equals plus minus pi over 2 of the arctangent function. And so the graph will look the following way. Let's say this is pi over 2 here. Correspondingly, let's say this is negative pi over 2. Arctangent of 0 is 0, arctangent of 1 is pi over 4. The asymptote should be 1 square up. So this is somewhere here is pi over 4, taken at value 1. And this here is the portion to the left of 0, which should be symmetric about the origin. That is the graph of arc tangent x. So these are the definitions of 3 most common inverse trigonometric functions: arc tangent, arc cosine, and the arc sine function. So what's left to do is to work through these many computational examples, which are very important. In fact, some of these examples we have already done. For example, we certainly computed arc sine of 1/2. We know that's 5/6. And remember, the reason was that first, sine of pi over 6 is 1/2, and pi over 6 lies in the desired range, negative pi over 2, pi over 2. We did compute arc sine of negative root 2 over 2. We know that's negative pi over 4. Again, the reason is that sine of negative pi over 4 is negative root 2 over 2, and negative pi over 4 lies in the interval negative pi over 2, pi over 2. What about this one? Arc cosine of negative root 3 over 2. Let me draw the unit circle. Centered at the origin. All right, so arc cosine of negative root 3 over 2. It's an angle, one of the angles, whose cosine equals negative root 3 over 2. Where is negative root 3 over 2 as the x-coordinate? It's somewhere here. And of course, there are multiple angles that have cosine equal to that. One of them is, for instance, 5 pi over 6. Another will be negative 5 pi over 6. And any other angle must be coterminal with either 5 pi over 6 or negative 5 pi over 6. And so, of course, there are infinitely many angles whose cosine is negative root 3 over 2, but only one of them lies in the interval 0 pi. That unique angle is 5 pi over 6. Cosine of 5 pi over 6 is negative root 3 over 2, but there are many angles whose cosine equals negative root 3 over 2, but only one of them namely 5 pi over 6, lies in the interval 0 pi. We did find arctangent of 1 and negative 1. We know that's pi over 4 and negative pi over 4. Arctangent. Arcsine of negative 1 we know is negative pi over 2. We found that too. Arc cosine of negative 1 is pi. Arc cosine of 1/2 is pi over 3. We did all that. Now these examples are much more interesting. For instance, what is arcsine of pi over 3? Well, given that sine and arcsine are inverses of each other, and the fact that pi over 3 lies in the interval negative pi over 2 pi over 2, arcsine of sine of pi over 3 simply is pi over 3. However, in the next problem, arcsine of sine of 2 pi over 3, if you simply write that this is 2 pi over 3, that will be wrong, because arcsine doesn't take values outside the interval negative pi over 2 pi over 2. You can take a look at the graph of arcsine. Arcsine is entirely between negative pi over 2 and pi over 2. 2 pi over 3 is, of course, outside that range. 2/3 is greater than 1/2. So, what should we do? Well, we can definitely simplify this a little bit and recall that sine of 2 pi over 3 simply is root 3 over 2. Two pi over 3 is in the second quadrant. And so its sign is the same as pi over 3. And sine of pi over 3 we know is root 3 over 2. But then arcsine of root 3 over 2 we know will be pi over 3. Certainly, sine of pi over 3 is the same as sine of 2 pi over 3. And pi over 3 lies in the desired region. Again, it's very important that you realize why the answer 2 pi over 3 is wrong. Arcsine of 2 pi over 3 is not 2 pi over 3. That answer is wrong. However, arc cosine of 2 pi over 3 certainly is 2 pi over 3, because cosine of 2 pi over 3 is cosine of 2 pi over 3, and that angle is in the interval 0 pi. Now, what about arc cosine of negative pi over 3? Well, if you want to say that this will be simply negative pi over 3, you would be in trouble. Of course, cosine of negative pi over 3 equals cosine of negative pi over 3. But the problem is that is not in the interval 0 pi. So we need another angle in the interval 0 pi whose cosine is the same as that of negative pi over 3. Again, the unit circle might help you. Here is the angle negative pi over 3. Of course, there are other angles. There's another point on the unit circle corresponding to the same cosine, namely this point. And of course, this point corresponds to the angle pi over 3. And pi over 3 does lie in the interval 0 pi. So we can say that our cosine of negative pi over 3 will be pi over 3. Just like before, make sure you understand very well why the answer negative pi over 3 here will be wrong. All right, what about arctangent of pi over 8? Well, that's simply pi over 8. There's no problem here because pi over 8 lies in the desired interval, negative pi over 2, pi over 2. But in the next problem, you can't say that arctangent of tangent 11 pi over 9 simply is 11 pi over 9 because 11 pi over 9 does not belong to the interval negative pi over 2, pi over 2. So the answer 11 pi over 9 will be wrong. And to figure out the right answer, again, we will use the unit circle. And where is 11 pi over 9? 11 pi over 9 is slightly above pi, so it's in the third quadrant. (11 pi over 9). Remember, tangents are along this axis. So this here is tangent of 11 pi over 9. It's a positive number. What about this angle? What's the measurement of this angle? Well, the measurement of this angle is 11 pi over 9 minus half revolution. So 11 pi over 9 minus pi. That is, of course, 2 pi over 9. So this angle here is 2 pi over 9. And note that 2 pi over 9 lies in the desired region and it has the same tangent as 11 pi over 9. So that gives us the right answer. 2 pi over 9, since 1, tangent of 2 pi over 9 is the same as tangent of 11 pi over 9. and 2 pi over 9 belongs to the interval negative pi over 2 pi over 2. All right. In the next set of computational examples, we might have to work with the right triangle occasionally. Say in the first example, we need to compute arcsine of cosine of 13 pi over 6. Because 13 pi over 6 is more than 2 pi, it makes sense to write the argument as 2 pi plus leftover. Of course, the leftover is pi over 6. Now, cosine is a 2 pi periodic function, so cosine of 2 pi plus pi over 6 is simply cosine of pi over 6. And cosine of pi over 6 we know is root 3 over 2. And our arcsine of root 3 over 2 we know is pi over 3. In the second example, let's figure out what sine of negative 11 pi over 4 is. Where is that angle? Negative 11 pi over 4. Well, negative 11 pi over 4 looks to me like negative 12 pi plus pi over 4. And that is negative 3 pi plus pi over 4. Because negative 12 pi over 4 is negative 3 pi. Where is negative 3 pi? Negative pi, negative 2 pi, negative 3 pi. And now from this point, we move in positive direction by pi over 4. So we arrive here at this point. Sine at this point is negative sine at that point, and that's simply negative root 2 over 2. That's negative sine of pi over 4. Which simply is negative root 2 over 2. And our cosine of negative root 2 over 2 is 3 pi over 4. All right. Sine of arc cosine of 4/5. What should we do here? Well, because arc cosine of 4/5 doesn't seem to be expressible in terms of fractions of pi, our only hope is to use the main trigonometric identity. Remember, sine squared plus cosine squared equals 1. So from here, we can express sine through cosine or cosine through sine. For example, sine from here is expressible as plus minus square root 1 minus cosine squared x. And so if I use this here, where instead of x, I have arc cosine of 4/5 in this formula, that will really be plus minus square root 1 minus cosine squared of arc cosine of 4/5. The question is, should it be plus or minus? Well, at this point we should recall that arc cosine of any angle, including of any argument, including 4/5, is in the interval 0 pi. That's the first quadrant or the second quadrant. And sine of anything in the first quadrant or second quadrant is always non-negative. So the answer better be a positive number. So therefore it has to be positive square root. And the rest is a technicality, because now we write that this is 1 minus cosine of arc cosine of 4/5 squared, and that is 1 cosine of arc cosine of 4/5 is of course 4/5. Now this is 1 minus 16 over 25. That is 9 over 25, and that is 3/5. There also is a way to solve this problem using right-angle trigonometry. If we denote t by arc cosine of 4/5, which must be between 0 and pi, then it follows that cosine t equals 4/5. And now, as you remember, cosine in a right triangle is the ratio of the adjacent leg over the hypotenuse. Our goal is to find sine t. Well, sine t is the ratio of the opposite leg over the hypotenuse. When the hypotenuse is 5 and one leg is 4, the other leg must be, by Pythagorean theorem, 5 squared minus 4 squared square root. And of course that's 3. So therefore sine t equals 3/5. That might be a little bit more geometric and a little shorter, as long as you remember and understand that the answer to this problem must be non-negative. That is because arc cosine is always an angle in the first or second quadrant, and sine of any such angle is always non-negative. In the next problem, let me add a page. We need to compute cosine of arctangent of 5/12. Again, we may use we can solve this problem in two different ways. One way would be to express cosine through tangent, and we can do this by using one of the identities. Remember, from the main identity, sine square x cosine square x equals 1, there follows that dividing by cosine squared, tangent squared plus 1 equals secant squared, or simply 1 over cosine squared x. And therefore cosine squared x equals 1 over 1 plus tangent squared. And therefore cosine x equals plus minus 1 over square root 1 plus tangent squared. We're going to use this here. If instead of x, you write arctangent of 5 over 12, that will be plus minus 1 over square root of 1 plus tangent squared of arctangent 5 over 12. Now, what about the sine? Well, arctangent, we know, is always in the interval negative pi over 2, pi over 2, and that's the first quadrant or the fourth quadrant. The cosine function is positive in the first and in the fourth quadrant. So cosine of arctangent of 5 over 12 is a positive number. We therefore take the plus sign, and then the rest is a technicality, because I can write that this is 1 over root 1 plus tangent arctangent of 5 over 12 squared, and this simply is 1 over root 1 plus tangent of arctangent of 5 over 12 is, of course, 5 over 12. And after some arithmetic, we get 1 plus 25 over 144. That's 1 over root 144 plus 25 is 169. 169 is square of 13. And so that simply is 12 over 13. Again, there is a way to solve this problem using the right angle trigonometry. If you let arctangent of 5 over 12 to be t, so tangent t is 5 over 12. And in the right triangle, that means that if t is an angle, tangent t being 5 over 12 means that the ratio of opposite leg over adjacent leg is 5 over 12. If we think of a right triangle with this leg being 5 and this leg being 12, of course the hypotenuse is square root of 5 squared plus 12 squared, which is 13. And we need cosine of that. So cosine of t equals 12 over 13 immediately. Okay. In the next problem, we need to compute sine of arctangent of 7 over 4. Again, there are two ways. One way is to express sine through tangent. And we can do this here. We can take this equality and work with it. Cosine squared is 1 minus sine squared. Therefore, sine squared here is 1 minus 1 plus tangent squared. Therefore, sine is plus minus square root 1 minus 1 over 1 plus tangent squared. What about the sine in this case? Because we can write that this now is plus minus square root 1 minus 1 over 1 plus tangent squared of arctangent 7 over 4. All right, where is arctangent of 7 over 4? If we draw the unit circle, it'll be arctangent of 7 over 4. It's an angle in the first quadrant or in the second quadrant, where tangent equals 7 over 4. So, of course, it's in the first quadrant. 7 over 4 is here. So it is this angle. It's in the first quadrant. So sine of that angle will be positive. And we should therefore go with the plus sign. And the rest is a technicality. So it's 1 minus 1 over 1 plus 7 over 4 squared. That's 49 over 16. (49 plus 16 is 65. So that's 65 over 16. So that is root of 1 minus 16 over 65. And that's, again, 65 minus 16. Root 49 over 65. And that is 7 over root 65. We can again solve this problem using right angle trigonometry. If we denote t by arctangent 7 over 4, so that tangent t is 7 over 4, as long as we understand that the answer must be positive, of course. So we're dealing with the right angle in which the leg opposite to angle t is 7, the adjacent leg is 4, then the hypotenuse is root 7 squared plus 4 squared. That's 49 plus 16, 65. And so sine t is simply 7, the opposite leg, over hypotenuse. 7 over root 65. So in the next example, we need to compute cosine of arcsine of 7/9. We already know that arcsine is always in the first or second quadrant, so this is always positive. I mean, the whole thing is always positive. Arcsine is in the first or fourth quadrant. Cosine in the first or fourth quadrant is positive. So now we replace cosine by the positive square root of 1 minus sine squared of arcsine of 7/9. That's simply 1 over 7/9 squared. That is 49 over 81. 81 minus 49 is 32. Root 32 is 4 root 2. And root 81 is 9. And again, a solution of this problem using the right angle trigonometry. If we let t to be arcsine of 7/9, so sine t is 7/9. So we have the right triangle in which the opposite leg to t is 7, the hypotenuse is 9, and so this leg is square root of 9 squared minus 7 squared. That's 81 minus 49, that's 32, which is 16 root 2. So of course cosine t is 16 root 2 over 9. Oh, over 9. Excuse me, that's 4 root 2. 4 root 2 over 9. Let's now talk about the last problem, arctangent of tangent 5. Unfortunately, this problem is often source of many confusions, so let's discuss that problem. Arctangent of tangent 5. It should be immediately clear that you can't say that this is 5. Because 5 is not in the interval negative pi over 2 pi over 2. So that cannot be right. So we can solve this problem in two ways, using the unit circle and then using the graph of tangent. Where is the angle 5 in the unit circle? Well, 5, I claim, is in the fourth quadrant because definitely 5 is less than 6, which is less than 6.28, which is roughly 2 times pi. On the other hand, 5 is more than 4.5, which is roughly 3/2 pi. If you view pi as roughly 3/2 pi will be 4.5. So in short, 5 is an angle in the fourth quadrant. Now, where is tangent 5? This distance here is tangent 5. Of course, it's negative because 5 is an angle in the fourth quadrant. Where is the angle arctangent of tangent 5? Remember, arctangent of tangent 5 must necessarily be between negative pi over 2 and pi over 2. So arctangent that corresponds to this distance, or angle that corresponds to this tangent, is here. And therefore, it should be clear from this picture that if I combine a turn by an angle of 5, let me call this green angle alpha. If this here is alpha, then the angle measuring the same number of radians, but in the opposite direction, will be negative alpha. Note that alpha is in the clockwise direction. Negative alpha is in the counterclockwise direction. So it's clear from this that if I combine the turn by an angle of 5 and a turn by an angle of negative alpha, which is again in counterclockwise direction, I get a full revolution of 2 pi. So in other words, 5 minus alpha equals 2 pi. So from here I can find alpha as 5 minus 2 pi. As expected, this angle is negative because we see this from the picture. The answer is not 5, but 5 minus 2 pi. And you can check. We need to check two things. First, that tangent of 5 minus 2 pi equals tangent 5. Well, that's for sure. Tangent is a pi periodic function, and tangent of 5 minus 2 pi is tangent of 5 minus pi. So that's tangent of 5 minus pi, which is same as tangent of 5. And second, we need to verify that 5 minus pi is in the desired range. 5 minus 2 pi is in the range of arctangent, which is negative pi over 2 pi over 2. Well, you can check 5 minus 2 pi is roughly negative 1.28, and pi over 2 roughly is 1.57. So negative pi over 2 is roughly negative 1.57. So of course, this number, negative 1.21, is between this and this. Another way to look at this problem is to use the graph of tangent when I'm thinking about arctangent of tangent 5. I can think of the graph of tangent. So that's pi over 2. That's 3 pi over 2. That's 5 pi over 2. And the graph will look the following way. There are these magic points. This is a little bit wrong. It should be here. Negative pi over 2. Now, this is pi, this is 2 pi, this is 3 pi over 2, this is 5 pi over 2. Again, 5 we know is between 3 pi over 2 and 2 pi. Doesn't matter where exactly, say this is 5. And this distance here is tangent 5. It's negative as expected. So I can draw this line here. That line has equation y equals tangent 5. Of course, that line, that horizontal line, intersects with the graph of tangent at infinitely many points. But only one of these points will be arctangent of tangent 5. And we know that will be exactly the point that's in between negative pi over 2 and pi over 2. So the desired answer is this distance. This here is arctangent of tangent 5. So how do we find it? That is the question. Let's again denote it by alpha. So by symmetry, this also is alpha. And it looks like well, if I view this as, as distance, alpha here is distance. So the answer is negative alpha, because it has to be a negative number. It's clear from the picture that 5, which is this distance, five plus alpha equals 2 pi. If you first move from 0 by 5, then by alpha, you get to 2 pi. The reason why this is alpha and this is alpha is by symmetry. Right? This curve and this curve are exactly identical. So by symmetry, this is alpha, this distance is alpha, and then this distance is alpha. And therefore, from here, alpha equals 2 pi minus 5, and therefore negative alpha is 5 minus 2 pi. It's just that here I denoted by alpha not this number, but rather this distance. I actually need the x-coordinate of this point. The coordinates of this point are negative alpha 0. So my answer is really negative alpha. 5 minus 2 pi. All right, hopefully these computational examples will be helpful. And this finishes our study of inverse trigonometric functions. Thank you.